What's going on, everyone? 1 second to close the door. All right. I'm going to pull up some stuff so we can get started. Our WSL environment, which I have since yesterday cleaned up and got all of my, or at least the important dot files moved over from the actual Unix stuff that I work on. We're good there. Let me pop open Microcorruption and get logged in while I am on the webcam view. And we'll get switched over in a second so that all of you can see my desktop. So, all right. We're going to switch this over. You do have good levels. We are good to go. All right. So, yesterday and the day before, or Sunday, I think it was yesterday and Sunday, we'd been working on Algiers. This was the first heap exploitation vulnerability, and I gave a brief description about the unsafe unlink vulnerabilities that were present in glibc, and talked a bit about kind of like how that kind of thing works. Since then, I've solved this. I ended up solving it last night. The general approach that I was on was sort of correct, sort of not correct. We spent a lot of time with let's just pop this open. Yeah, there we go. We got like actual vim config. We spent a lot of time trying to overwrite these backwards and forwards pointers, trying to get the pointer update to write to the return address during the code, basically in the consolidation steps. So like in this case, if it was going to consolidate forward, it would be here. Backwards, it would be, I believe, here. And so we spent a lot of time trying to make that work, and we started getting into these situations where, like, when it would do the first consolidation, we'd get it in the right spot, but the second consolidation would break it, or we'd end up doing the consolidation and writing to the stack, but we'd end up corrupting the code segment, which was a problem. We couldn't figure out exactly what to do. And part of the problem and why this didn't work is that the way that this C code works under the hood in the assembly, we can go to, where's the free implementation? Where's free? Free is here. The way this ends up working is in this move right here, this move R15 to the previous pointer. So it goes back one and sets the previous pointer. And part of the problem is that we don't really have control over R15 ever. This is the pointer that comes in from the user, like in the code. So we don't really get to change this, and so we don't really ever get to take advantage of this, and that was part of the problem. The thing that I overlooked the first time and kind of just on a whim, just like, I'll try this. Like it seems like it would work, but it's kind of hacky and messy. The thing that we do have some ability to control, though, is the size field. So when it does consolidation, it needs to update the previous. So if you're consolidating backwards, it has to update the size field of the previous chunk with the new size, with the adding on like the current size field. So it says, I'm the previous chunk and the one after, and now it's that full size. Or if you're going forward, then you get the next one and you take its size and add it to yourself. And that is something that we do control. We sort of have the ability to kind of like write anywhere with that because we control the previous and the next pointers. So if we set the previous pointer to, in the case of like backwards consolidation, if we set the previous pointer to be the stack address on the heap, when it follows that and tries to write it, it's going to write the size there. Sorry, the return address on the stack. So the problem here is it's a little bit off because the size field is the third word of the pointer. So we would need to move this forward a little bit. So I'm going to, we'll set a breakpoint like, where is login? Login. I think this is fine. So we basically need to set it 3 words ahead, which ends up being right here. And if we set the previous address to that, it follows that and updates the size field, which ends up being here. Then we just need to trick malloc, or free, into thinking, we don't trick it. We overwrite the size field, and when it adds up all the values of the different chunks it's going to do, it's going to write in that value there. And we just need to make sure that the value, the size, the eventual size, ends up being the address of the thing that we want to jump to. That's what I ended up doing in my exploit here. So this password isn't actually necessary. You just can't send an empty value when you're in hex mode, but if you're in character mode you can, and I was already in there, so I just did it. So when we put in the username, we end up overflowing username. So this is just 16 A's. We don't need anything in here really, except for this, and I'll explain this in a second. Right here, this 4E 00. But we end up setting our previous pointer to be this address on the stack right here, which is 4396. Our next pointer ends up pointing to into our string here, and I'll explain why in a minute. This doesn't necessarily matter, and this can kind of be garbage. And this is our new size field. We're writing BC here. It took some working. I had to get the math right, and what I found was that by just adjusting this one, I couldn't quite get the value that I needed. Adding the 6s and combining like the other chunk, I just couldn't quite get the value right. And so what I ended up doing was setting my next right here to be the beginning of the string, which 3 bytes in, or three words in, I can put another size field here, and just having this second size field and consolidating that as well allowed me to kind of get a value that let me have what I actually wanted, which was the address of unlocked door, which is 4564. So I can walk through this, and we can check this out. I'm gonna do a reset on that. I'm gonna do the break, remove it from here, and we'll break. We're not gonna bother breaking on this free because this free, like the password doesn't actually do anything. We don't have any kind of overflow there. Sorry, no, I'm wrong. That one is the important one because we're overwriting the metadata for it. We don't care about this one because nothing's going to change here. I don't believe. I'm going to continue there. I'll put this into hex. And continue to 42. And so we're at the point where we're going to call free. We see that we have overwritten the previous right here, which points to right here. Our next is pointing to right here, and and this is marked as free. So yes, sorry. For E is 0 in the 1 place. So this is marked as free. It's just a free chunk, and we have not touched any of this metadata here. So I'll jump into this. And this is the first part of the consolidation. This is consolidating backwards. And I'm going to kind of gloss over a little bit of this because we don't really need to know that much. But I am going to stop right here. We can see R14 240E. It's right here. And it's going to end up writing this new size field. We're going to move on to the next consolidation. And so we've already seen this get updated. We're going to move. And we're doing some addition there to update the size field. We're adding the 6. And this R13 right here, 4564, this is the value that we want. We can see this is getting moved right to there. So when I hit next, it's going to update for us, sorry, down here. And now we've overwritten the return address. So I'm going to not bother with that. We'll step out of here. We're not going to update again. And I'm going to finish. Step, and we're at the ret, and it takes us to unlock door. I'm going to continue here, and we'll see what we finish. So that's how I ended up solving it. I ended up looking up some answers after the fact, and it seems like most other people ended up doing the same sort of thing. Some others didn't have this problem that I did, where they were able to put in like just a value right here that ended up being correct. And I'm not exactly sure why what I had here wasn't working. It may be that like the values are slightly different from player to player, and so mine just happened to be such that I couldn't do that. I didn't spend a lot of time like once I got it like trying to like clean it up. Apparently there are solutions that are a little more efficient, but I didn't look into them really. I was happy that I got this working and didn't really want to like spend too much more time on it. It made sense, and I was like, yeah, it's not elegant, and I honestly thought it was kind of like a janky exploit until I looked up what other people were doing, and I realized that like they were doing the same thing, and I felt a little bit better. I'm still kind of curious if it's possible to do the forward and back pointer overwrites and get that to work without doing the size. But I'm honestly not sure, and I'm not planning to go back and do it right now. So I'm going to move back over to our doc here. I've already updated Algiers and did the write-up, and this kind of explains like everything that I just did. So this makes the size field of the new previous chunk point to the return address, blah, 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 blah. Yeah, so that pretty much covers like the part for Algiers. I haven't looked forward really yet because I wanted to save the rest of this for the stream because I wasn't really sure. I think there's only a few challenges left. If we go to like Hall of Fame, I think we can see it. Just grab like the person who's in first place. So it looks like there's 1, 2, 3, 4, 5 left. So maybe we'll get one done today or two. I don't know how long it will take us. But we've got these 2 left available to us right now. I think once we solve either one of these, more open up. I'm going to check out this first and we can see like what they each are. I'm not sure if we're going to have more heap exploitation, but having like that document there will probably make it easier if we do. I'm going to actually pull the manual up again. What changed here? So this is NHSM 2, which the other one wasn't. So the big difference between the HSM 2 is that it automatically does the unlock. So this is probably going to involve some shell coding because we're not going to have a like a straight up like function to unlock the door. It looks like there's ASLR here of some sort, and this looks like it's encoded somehow. This looks like it's all printable, and it's building up a string character by character. Great. This is also printable ASCII, and this is a null byte, so that makes sense. So 2402 seems like it's a scratch pad for a string, because it starts here as well. More printable ASCII. All right, so maybe we should bother with just decoding that and seeing what it says. This is Maine, and it looks like it's doing a mem copy. So it's copying hex 1000 bytes. Is source destination or destination source? I always forget that. It's destination source. So this is going to be the destination and this will be the source. So init stack. That's interesting. 4,400. I guess it's copying those bytes into whatever R11 is. Okay. Well, let's start by I guess just like figuring out what this says. That seems like it's going to be the most straightforward thing we can do to begin with. I'm just going to open up Ruby and we'll just kind of like do what we've done in the past. 73, 65, 62, 61, 60. I'm sure this is probably just like an enter your password or something. This is a space. I think this is like a quote or something. I forget what 20 it is. 38. It's another space. 63. 68. 61. 3A 0, and then 17 is not sure what this hex 17 is. It's 23. Oh, you know what? It's probably that many bytes. Yeah. So it's a length prefixed string, which is fine. And it doesn't. Oh yeah, it does it here. So it's 10. 1, 2, 3, 4, 6, 7, 8, 9, 10. 50, 61, 73, 73. That's probably S's. I think it's just gonna say password. 6F, 72, 64, 3A, and Arnold bytes. Yeah, just says password. So it's doing some string building. I'm curious how it gets into this function. My guess is if this is Maine, it's probably right here where R13 ends up having the address of ASLR Maine. R13 64B6. Six, 4, B 0, 1, 2, 3, 4, 5, 6, 4F, Six, 4, 6. Let's, I guess, start at the beginning of Maine and let's see what it's doing. That might be the most useful. It looks like it's calling rand. I'm curious if it ever makes it into ASLR Maine, or if it's just copying data out of there. Oh yeah, it overwrites like. So it zeroes out. It zeroes out all the instructions, and then loads it up at a different address. That's so interesting. That's kind of cool. Um, so there's a few things you might want to look at. One is, can we predictably tell what the address is going to be? And we might be able to do that because it may be that rand is deterministic, and because we're like it's not providing like so. Typically, when you call rand, you're going to seed your random number generator when you start up the program, so that every time you run it, you're going to get a different value. I guess before we dive into this, maybe it makes sense to explain like what ASLR is. So ASLR is address space random layout randomization. The idea is that it can shift around the address where your program starts at, so that your return addresses are not reliable. This was one of the countermeasures that was added to Linux and other operating systems a long time ago, at least 10 years now. It's been a technique for a long time, but the idea is that if you can't predict where the overwrite is going to be or where your shellcode is going to end up, you can't return into your shellcode. And there's different techniques that have been used to bypass that. One of them is ROP. I kind of doubt that we're going to have to build a ROP payload here, but it's possible. We might end up having to do that. And so the ways that you typically defeat ASLR is by finding areas that are not randomized. So sometimes like the whole program will not be randomized, or it will only be randomized like every time it starts up. So if your process forks, multiple connections may not change the randomization. So if you can leak it and then reconnect, you can do that. So we might be able to leak the address. The address may be deterministic in terms of like where it relocates the program to. Or maybe there's another thing. I think that at this point we just need to kind of like dig into here and see what it's doing. So it looks like 6050 is the address that it ended up putting it at. If we restart this, oops, continue. Wait. Yeah, so it looks like it's not determinate. It's not deterministic. It's not going to be always be the same spot. So it ended up relocating this to 64E0. 3041. So we'll reset. Let's walk through this and see what we can figure out. I'm gonna get rid of this. So we get into Maine pretty quickly. What's up, Pookie? And we're gonna call Rand. So we're not doing srand, which is interesting, and that I said that might be one of the things that we can key off of. But it's because it's changing every time, maybe not. R15 should have our value in it, so we're gonna step finish. So it ends up having 0 dd0. We can reset it and see if it changes. Yeah, so it changed every time. So that gets moved into R11. And then it takes 7FFE and it ands it. And then it adds hex 6000, which is kind of weird. I wonder like why that specific like things. So let's we're not gonna need that right now. So 7FFE. I'm not exactly sure why they're choosing this value to AND it against, but R11 is 4C73. Oh, I see what it's doing. It's getting rid of the this is relaxing. So what this is doing is it's getting rid of the low bit, so it's making sure that I think it's aligned. So E is never going to have the low bit set, so the AND will always mask off that that low bit. If we look at like what this is as a in binary, it'll make a little more sense. So 7 would be 0, 4, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3, 4. And then E is 1, 1, 1, 0. I'm not sure why it's getting rid of the high bit as well. Maybe that has some specific use or something. I'm not sure. Or maybe it's to make sure it can't overflow or something. But basically what it's going to end up doing is making sure that we're at an even number. And we saw this yesterday when I was talking about like alignment with our instructions. Is that the way that MSP 430 works is all instructions are 2 byte aligned. So they're either 2 bytes or 4, I believe. I think 4 is the max. So this is going to ensure that our address that we're like the value that we're grabbing from Rand is going to have a even number basically. Then it's going to add 6,000 hex, which I mean this must just the reason it's masking this off must just be that we don't overflow, I guess. So it keeps it on the like the higher end, which I guess that removes a lot of entropy because we know that it's going to be something higher than that. It's not going to wrap around. So R11 is AC72. It's going to call rand again. Finish. DD3E. And then that saves it into R10. We're pushing hex 1000. Hex 1000 is, I think, 4K. I always have to do the conversion on this because I never remember. Yeah, it's 4K. So we're going to copy, if we look at memcopy, memcopy is destination, source, and then the number of bytes. So we're going to copy 4K bytes. Our source is going to be from 4400, which we can see right here. What is 4400? Basically, it's grabbing all of this data, everything except for this the trap interrupt is getting randomized. It looks like. And so we're copying 4K from the beginning of like the program effectively. And then R11, so the first random number we get that does all this shit, that's where we're gonna copy the program to. So push, push, push. We're gonna call memcopy. I'm gonna finish that. That's super slow. So AC72, AC7, yeah. So this is just a whole bunch of zeros right here in our address space. And then this is the beginning of what we just copied. So if we go up to the top here to 4400, we should see like basically this. So we've just copied over the entirety of the program. We're gonna add 6 bytes to the stack pointer. So basically we're just getting rid of all this stuff that we just pushed on, I think. Yeah, so we've just subtracted off all the stuff we passed onto the stack. R10 has the second random number that we grabbed. So we're moving that into R15. Again, we're gonna mask off the 1 bit, so we're gonna know that this is an even number. And we're also masking off the entirety of the high byte, because this has an implicit 0 in our most significant byte. So this became 0D 3E. E was already even. And then we're moving R11, which has the place that we relocated to. That's going into R14. And then we're subtracting 15 from 14. And then we're adding... Why FF? That's interesting. And we move it into R11 into R13. And we add hex 35C to R13. AFCE. This is just to get us to the right place into our code. If we look at 440, that plus 35C. What did I do here? I forgot that 475C. Four, 7, 5C. So yeah, it's basically is jumping into ASLR main here. All right, one sec. Oops, we don't want that. So, still not sure what the R14 is for yet. I assume we'll figure that out. Oh, this becomes our new stack. Is it 9E34? I wonder if the reason it's doing this is to force an overflow because it knows that this is going to be lower than where it just relocated the application to. Because that seems like what it's doing. R11 goes into R15. Which means that we're passing in R11, which is the... is that where we relocated to? Or is that where the new... AC72... Yeah. So it's just telling ASLR main like where the start is basically. We're not gonna be able to follow it. That's so irritating. What I might end up doing to make this easier to do is move all of this over into a binary that we can just relocate into Binary Ninja, and that way we don't have to trace this like through here. But I think that makes sense to do off stream. It just doesn't seem like super interesting. So I might do that later tonight, and I think we'll pick this up another time because I don't really want to sit here and like go at like instruction by instruction through here and try to remember like where I'm at and do the translation myself. So yeah, I think we'll call it here. I got to explain a little bit how I solved Algiers, which I think was like the big thing I wanted to cover, and start taking a look at like what we're seeing here. So maybe later tonight we'll pick it back up if I can get this done early enough, or probably like tomorrow, or maybe some Christmas streaming we'll do. Anyway, happy holidays to you, Pookie. I hope you have a good Christmas and get to relax. Have a good rest of your day, everyone, and let everyone know if I'm coming back on tonight or probably tomorrow, most likely at this point. Anyway, have a good one, everyone.